forget what I learned. Want this off? Yeah, no, that was my discovery today. Good evening, and welcome to the Wright Brothers Lecture in Aeronautics. We're pleased that you could join us. My name is Rodney Bowersox. I'm the Aviation Forum's General Chair. This lecture commemorates the first powered flights made by the Wright brothers at Kitty Hawk in 1903. This is one of the most prestigious awards given by the Institute and emphasizes significant advances in aeronautics. I'm very pleased to introduce our distinguished lecturer, Mr. Justin Paynes. Justin is the Joby Aviation Chief Test Pilot. He received his education at the University of Oxford and then at MIT. He joined the Royal Air Force in 1988, where he was posted to the #1 Fighter Squadron Flying Harrier aircraft. Justin attended the U.S. Air Force Test Pilot School, class of 1995. He began his career as a test pilot at Boscombe Down in Wiltshire, England, with the principal responsibility for the Harrier experimental fly-by-wire aircraft. He also flew all marks of the X-35 through the Joint Strike Fighter Concept Demonstration Program. He served as an instructor at the Empire Test Pilot School, including 2 years of chief flying instructor, and recently joined Joby Aviation as the chief test pilot in 2018. I now invite Justin to the podium. There's Justin. He's going to speak on turning flight control on its head for the F-35, eVTOL, and beyond. Justin, it's all yours.
Thank you very much. Thank you very much, Rodney, and I'd just like to say very briefly how very privileged and honored I feel. This is, you go through your life in aviation, you do your best, and for people like those who nominated me for this award to turn around and honor me in this way is massive and probably largely undeserved, because all of these things are a team effort. It's never down to one individual. And I'm very, very honored and grateful for this award. And I hope I can give something back now by talking about the work that we did. And I'm going to talk a little bit about the past. And this is the main reason I've been asked to speak and what I've been given this award for, which is the revolution in flight control that we developed for the F-35 Bravo. That's the STOVL, short takeoff, vertical landing version of the F-35. What we did, and it was quite a revolution, and so were we right? The jury's now in. I'd like to talk a little bit then about the present, the urban VTOL, eVTOL revolution that's going on right now, and what the work we did in the past, how that applies to what is going on right now, and look a little bit beyond as well to the future with another revolution that I'm going to argue is needed in commercial air transport pilot vehicle interface. So with that said, let's start with the story of the flight control system for the F-35. And of course, the UK had a long history of research and development in VTOL. You can see the flying bedstead there at the top, and then of course the P1127 bottom right, and then leading to the Harrier. And the Harrier was a huge triumph in aviation, arguably the only successful STOVL fighter, or VSTOL fighter, certainly the only successful one in the West. And the great news about the Harrier was the simplicity of its engineering that with only one extra lever in the cockpit, as my mentor John Farley used to talk about, the addition of only one extra lever in the cockpit turned a regular fighter from a flight control perspective into a vertical takeoff and landing aircraft. And tremendously ingenious mechanical engineering throughout that vehicle, not a digital computer in sight. But there were inevitable compromises in the aircraft as a result of this. It was, of course, the pilot had independent manual control of the throttle, of the thrust magnitude, and of the thrust vector angle, the nozzle lever. And so it was a high workload aircraft with the risk of cognitive errors being made by the pilot. And you're going to see one here. This is an air show about 10, 15 years ago. A very experienced pilot is the squadron air show display pilot in a 100% serviceable, functioning Harrier off the coast of south coast of England. Nothing wrong with that aircraft at all until now. So a perfectly good aircraft thrown away by an experienced and capable pilot due to cognitive error. He pulled the throttle back instead of the nozzle lever. Sounds like an obvious error to avoid, doesn't it? But he's not the only person to have done it. And it's not the only form of cognitive error. So we have a great capability in the Harrier, or had, but we had an accident rate in the takeoff and landing regime, an accident rate that was an order of magnitude higher than the accident rate for equivalent conventional takeoff and landing fighters. A 10-fold accident rate for takeoff and landing. We had a significant training burden. So the Harrier training course, you came out of the training system with your wings, went to the Harrier. It took 8 months to graduate as a Harrier squadron pilot. Compare that to equivalent conventional fighter aircraft, about 3 months, 3.5. So significant training burden. And then we carried operational limitations, both in terms of having less good weather minima than compared to, for example, a helicopter, which you could argue might have similar weather minima, but we were less able to cope with bad weather in the Harrier because of the high workload. And we carried a performance margin to take account of the variability in pilot technique. And we also had to send only better pilots to the Harrier. We couldn't send a cross-section of the training output because we found that the weaker half of the training output simply wouldn't cope with the high workload in the Harrier. So we had a significant pilot selection constraint too. So necessity is the mother of invention, as the proverb goes. We had a problem to fix. And so we, the US and UK governments, that were both operating Harriers by the 1980s, set out to fix it. I picked up this program in the mid-1990s. The Joint Affordable Strike Technology Program was just at that time morphing into the Joint Strike Fighter Program, where we were going to have complex lift systems that were going to be digitally controlled. There was no option anymore for a simple mechanical lever between a nozzle lever in the cockpit and the thrust vector angle. But we didn't start from scratch. There'd been a lot of work done through the 80s and early 90s. But from 1996, for 10 years, there was a joint aeronautics program between NASA and the Royal Aircraft Establishment in the UK, both countries pursuing VSTOL, advanced flight control research. Shared facilities, shared data. You see at the bottom there the NASA VSTOL systems research aircraft, and to the right, the VARC Harrier that I'll be talking about a little bit more. So up until 1996, when I'm going to pick up this story, there'd been a lot of work done. And what had we learned in that period of time? What did we know already from the research that had gone on up until 1996? The first thing we'd learned very, very clearly, unequivocally, is that decoupled axes greatly reduced pilot workload. By decoupled axes, I mean if you look at a coupled axis in a normal airplane, if I push the throttle forward, I go faster, but I also climb. So the axes are coupled. And what we found is by decoupling the axes, so if I make a command to the airplane to go faster, my flight path doesn't increase. I don't have to retrim as I go faster. For example, by decoupling the axes and allowing the pilot to handle one axis at a time effectively, we greatly reduced his workload. We also found that higher levels of augmentation reduced workload significantly. And by that I mean you give the pilot control of the output variable that he's intending to control. So you give the pilot direct control of speed or acceleration, or you give him direct control of flight path angle or flight path rate, according to the task at hand. You'd never want to give him control of the elevator or the ailerons and have him perform the control loop around getting the response out of the aircraft that he wants. Particularly fine work from NASA in some of these areas, and they came up with translational rate command, which I'll talk about in a little bit, which is now almost universal in hovering aircraft, and developed at NASA Ames with some really stellar work from the guys there. So that's what we knew in 1996, but there was a fundamental challenge that remained. And that is that a VSTOL aircraft is really two vehicles in one. Hover and forward flight are two fundamentally different flight regimes, not only in engineering terms, it's obvious, but in terms of the task that the pilot is trying to accommodate. In wing-borne flight, he has a vector to control. He's going up, down, left, right with his vector, and now how fast he wants to go. But he's controlling a vector through the air. Whereas in the hover, the pilot is now controlling a position over the ground, an XY position control with a secondary height channel control margin. He's not trying to control a vector, but a position, and in a completely different plane. We look at the flight path control plane is like this. The hover control plane is horizontal. So two very fundamentally different tasks. And in a traditional aircraft like the Harrier, you would blend between them. So on the right of the screen there, you see wing-borne flight. If I push the stick forward, I reduce my angle of attack, I go down. I decrease my flight path, at least in body axis terms. And then when I get to the hover, if I push the stick forward, I accelerate forward. And in between the two, we blend. As the speed slows down, so my flight path response decreases and my fore and aft X acceleration response increases. And so we blend seamlessly between those two command strategies. But of course, that blend is dependent on the axes being coupled. And it also arises in higher workload for the pilot because he's having to manage a changing vehicle and brings cognitive confusion into the game as well. Now, as soon as we decouple the axes, we can't do that anymore, which is no bad thing because we've already decided it's a high workload task, but it also now becomes impossible. Remember, we'd already decided, previous work to 1996, decoupled axes are better. Well, if we're going to decouple the axes, we cannot do what the Harrier or the helicopter does, which is a blended transition with both axes being coupled. So this is the aircraft that we did the work on, the Bedford VARC Harrier. It stands for Vector Thrust Aircraft Advanced Flight Control with a soft small T and F to make it an acronym that is pronounced VARC. That's about 1996, before the color scheme was changed, and that's actually at Boscombe Down after it moved there in 1996. Fairly ordinary on the outside. It's actually the oldest two-seat Harrier still in existence. That was built in 1969, one of two original development batch two-seaters. After it had finished its work with Hawker Siddeley, it was given to the Royal Aircraft Establishment, became a research aircraft. And of course, the magic's on the inside. It's just a regular Harrier on the outside, and you have a rear cockpit there. That's the rear of the two cockpits with variable field center stick that was we later installed an active side stick, a left inceptor quadrant that could be pulled out. So by inceptor, by the way, I'm just talking about a throttle or a stick, something that the pilot holds to make inputs to the flight control system, are generically called inceptors. But the main thing about it was that we had non-safety critical software. So we could not only turn around a software build in the morning, load it on the airplane and go and fly it immediately without any regression testing, without any safety testing, but actually in flight, we could sit in the rear cockpit flying in the hover and adjusting parameters within the flight control system. We could vary a feedback gain, a command gain, or anything else we wanted, turn features on or off, real time in flight, made it very, very fast to make progress. We just can't do that, of course, with normal flight control with all the safety mitigation or regression testing that is required every time we roll software. But a very, very flexible tool. So what then did we do with it? So remember the fundamental challenge that I introduced a couple of slides ago is linking the hover with wing-borne flight and doing it in an intuitive, low workload manner that works for the pilot. How do we link the hover and wing-borne flight regimes in this kind of aircraft? Well, we identified candidate solutions. So we did a lot of brainstorming. We looked at the work that had been done before and the different implementations. We looked at different aircraft types. Of course, most of the mechanical had some kind of coupled axes, but we could still draw lessons from them. And we came up with essentially two main types. There were actually three to start with. We threw one out after fairly early flight testing. And we ended up with two fundamental overarching solutions, and that is you either change what you do between the two regimes. So you might have a conventional fighter, fast, slow, up, down in wing-borne flight, and then when you get to the hover, somehow you engineer a change so you've now got up, down on the throttle like a helicopter or Harrier, and left, right, up, forward, back on the stick. And without going into further details, it'll be in my written paper, but you have to introduce a third inceptor to do that. But there is a way you can do that with decouple the axes if you introduce a third inceptor. Or you go for something different. You go for something where you unify the response of the aircraft to the cockpit inceptors, irrespective of speed. And we called it Unified Flight Control. It was actually invented in 1980 by Peter Nicholas, one of the guys that worked a lot on the Joint Aeronautical Program. Unified Flight Control, quite simply, is, well, if I pull the stick back, the houses get smaller. If I push the stick forward, the houses get bigger, which sounds quite familiar, doesn't it? The difference is that this happens whether you're at 5 knots or 500 knots. We're using the aircraft's flight control system to engineer it such that the vehicle maneuvers in the same axis for the same lever being moved, irrespective of speed. And on the throttle, if I push the throttle or the left inceptor forward, I go faster. And if I pull it back, I go slower. Or if I'm in the hover stationary, if I pull it back, I go backwards. So we've unified the controls. They operate in the same axis, irrespective of the speed of the vehicle. Which is a pretty unusual thing for anyone who flies helicopters or Harriers. And we'll come on to that in a moment. So these candidate solutions were implemented in the VARC Harrier for evaluation. And this is the key. The experiment then was piloted evaluation of handling quality tasks. When you do a piloted evaluation of tasks, it's very important to get the task set up, the experiment set up right, because obviously if you get it wrong, human beings are very subjective, you can easily swing the results one way or the other. So the task definition is crucial. You have to come up with a task that is number one, relatable to the mission or the role that the aircraft's going to have, that's representative, that's not some kind of artificial task. And you need to generate a task where the pilot will be operating in what's called high gain. So a human being has a gain in the same way that a control system has a gain. And human beings can become high gain controllers in different environments, normally when the visual cues are more compelling, or when there's more stress, or when there's a tighter tolerance required on human performance. We need to go to high gain because it's high gain tasks that elicit the deficiencies in any control strategy. And we needed to make the tasks representative, but also ones which would test the parts of the flight control strategies that we were looking at in the most demanding way. We wanted to probe the weaknesses in each of these strategies. We used an industry standard scale, Cooper-Harper Handling Qualities Rating Scale, which was designed in the 1960s, and a NASA report there. You can use that. It's very much industry standard, nothing particularly new there. And we used multiple test pilot evaluators. So trained test pilots are trained to be objective, at least as much as possible. And we had both Harrier experienced and non-Harrier experienced test pilots flying these tasks. So what did we use then for these high gain but mission representative tasks? Well, the first thing we did was we picked up these visual targets that had been developed in NASA in the 1980s. And what they were is just visual targets that allowed you to make the pilot perform in a high gain way, but when you're clear of the ground. So normally you don't get good visual cues in a Harrier until you're getting close to the ground. You've got ground effect, which is nasty in a Harrier. You're outside the ejection seat envelope. And so NASA designed these targets to provide a visually compelling high gain task away from ground effect. And we found them on a dusty corner of Moffett Field, looking a bit sad and unloved. We shipped them over to the UK in a US Navy C-130, painted them up and put them back into action, which was rather nice to do. And we also took the vehicle to sea. So Her Majesty's Navy gave us access to HMS Invincible on a couple of or three occasions. And so we were able to perform tasks at sea as well. And the advantage of that is that the task is naturally a high gain task on a rolling pitching deck at sea. You've got superstructure very close to you. You're much lower and closer to the deck as you come across it. And it's a much higher gain task for the pilot. So it was a great place to evaluate our control strategies and to compare the two that we were looking at. Just going to show you a quick video. There's no sound on this. This is so up the top of that crane. You see the NASA targets that we rescued from Moffett Field, and this is the aircraft coming to a stop. And there were different sections of tasks. So this first task was basically a longitudinal position capture, simulating coming in to the hover and stopping a beam the beam, if you like. The next task was a lateral position capture, and you'll see the aircraft in a moment cut across and capture those targets. There's a lot more noise in real life, of course. This is before the era of GoPros and so on, and we had to put a camera at the top of that beam, of course. Then there's the problem of remotely switching it on. I mean, everything's so easy nowadays. Back in those days, we couldn't remotely switch the camera on. So we did try to persuade one of our flight test engineers to go up onto the top of the crane and on the beam, but sadly he refused, so we just left the camera running. And then in a moment, you'll see the aircraft begin its descent to the pad. So that shows there's about 3 or 4 tasks in that the pilot was undertaking, and we'd run him through identical tasks using the different control strategies. He's now just positioning for a final landing, which you'll see in a moment. And on this final landing, the intention is for the pilot to put his head in the middle of the square pad you'll see in a moment. So it's not to put the vehicle in the middle, but he's trying to put his head in the middle of the pad. So what results did we get? And in those few minutes of talking, of course, were years of effort and millions of dollars of our respective governments' money. And unfortunately, obviously, limited time, I can't really go into a lot of the details. I will attempt to put them in the written paper. But the summary, in cutting to the chase here, is that the results strongly endorsed unified flight control. So we anticipated difficulties with unified for the XY position control in the hover. So everyone said, oh, it's much better in the hover to have XY position control on the stick, on one inceptor. So I go forward, back, left, right, or at a 45-degree angle. Very intuitive, very simple. If I'm going to split them between 2 hands now, so I'm going forward and back here and left and right here, that's going to be harder. Well, we simply didn't see that that was a challenge. If there was a degradation in handling qualities or increase in workload, it was very, very small, minor, and easily outweighed by the massive cognitive advantages of the simplicity of the control strategy. The pilot knew whatever speed he was at, or if he didn't know what speed he was at, he knew that if he pulled back on the stick, his flight path would go up or his height would go up. And if he pushed forward on the throttle, he would accelerate along the flight path vector. So very strongly endorsed and backed up by a wealth of in-flight research data that, as I said in this presentation, I can't really give you a lot of the meat and potatoes. However, vehemently opposed by some in the pilot community. And this is sort of turning to the topic I'd like to cover through most of the rest of my presentation, because this is a really excellent example of predisposition and paradigm. So this was vehemently opposed by some, and a bitter debate ensued as a result of it. So the legacy control community, if I can call them that, people who were used to helicopter and Harrier-style controls, just couldn't accept that they could get away from an XY control in the hover on the sticks. They can do a 45 left or a 45 right, and everything's nice and intuitive on a single stick. And they couldn't understand, well, I pull back on the stick and the engine spools up. That makes no sense at all. And if I want to do a 45 translation, I've got to use 2 hands. So these were the sort of arguments raised, and there were some that would not be persuaded. So after 2 or 3 years of fairly emotional debate, and it literally was 2 or 3 years as the results came out and the data came out, and many of these pilots that argued against it were our subject pilots in the experiment as well. A grade beard panel was convened by the Joint Strike Fighter Program Office in 2002. We took 3 or 4 days presenting our various bits of data, and those who were arguing for other ways presented their data, and eventually unified was, or at the end of that week, unified was chosen. But it did feel a little bit like this much of the time. The question, though, is, were we right? And, of course, the jury is now in. The F-35B has been in operation for some years, and I'm going to cover that in just a moment. Before I do, though, just going to show you a bit of footage, and there is some sound on this. I'll let the pilots chatter away. You'll hear they're quite happy. So this is Peter Wilson, who's been flying the F-35 the last 10 years, and actually has just joined Joby Aviation as well. And Chris Gotka, Sea Harrier test pilot, who's the safety pilot in this evaluation. So Pete Wilson is the subject pilot, and Chris the safety pilot. I'm going to let it play for a bit, and then if you'd stop it for a moment, then I'm going to just describe the head-up display symbology. But let's just play for a couple of minutes, and then I'll stop it.
Do you have control? I have control. I track engage. I track with GOT. Just going to point it slightly to the right. Right, come forward to the board. Coming forward to the board.
Okay, if you pause it there.
Switching the gripper on, gripper we've got.
I don't have a pointer, I don't think, do I? I should have. I'll try and describe it. So if you look in the middle of the display, just above the horizon line, there's just a little solid circle. That's just a fixed attitude reference. It means nothing more than that. The diamond-shaped symbol with wings that's level with the horizon there is our height rate marker. So for every degree of depression, and you can see the 5-degree bars down below, that's 100 feet per minute. And then out of the center middle of the screen at the top, you can see a line going off just left of true north. That is a God's eye view velocity vector. So that's showing that the vehicle's traveling forward at 2 or 3 knots, going almost straight forward, but just a little bit to the left. And the little circle that's at the end of that velocity vector, God's eye view velocity vector, is the command. So as the pilot makes the command, you'll see the smaller circle move fairly quickly, and then the vector follow up as the aircraft responds to the input. And I'll just let it play if you go ahead.
Nice gentle movement with about a 5-pound forward force. Releasing. Picked up the board spot on. Can't make that better. Going backwards to pick up the yellow line, and then about to come laterally right.
Happy.
Roger that. That's just giving us about 4 knots backwards, and that's about it's about a pound per knot, it feels like, so that's pretty good. Coming to the right along the lines. Good little kick there. No doubt you've put in the lateral input, which is nice, good feedback. And then it just takes it up to about 2 degrees of bank. That's for 4 knots. That's probably about a 5 or 6 pound right force. Slightly low in height, but the gripper's got me nicely. Getting the rates. I'm just going to take gripper out and just adjust the height slightly, and then put the gripper back in again. Hear the engine RPM note, and we're smack on where we need to be. Coming to the right.
Cheese.
Indeed. And then getting very used to the amount of anticipation required. This is the most accurate I've been all week, so it's phenomenally impressive. A bit more aggressive to the left, but ever so easy to get used to the anticipation required. That's just awesome.
You can go across the boards again if you want.
Can I?
Yeah.
Okay. I'm going to go 4 and aft again, if I may, from the pad.
I think you get the impression there. So that's just an interesting little insight into what we're doing and the sort of comments we were getting. So were we right? Sorry, I've gone the wrong way. Nice picture of the F-35 on HMS Queen Elizabeth just 6 months ago. Pete Wilson is in the jet that's on the deck, and one of his colleagues alongside there in the hover. A beautiful picture. But were we right? So we did, first of all, Lockheed Martin, just down the road here, obviously did an amazing job implementing the flight control strategy. So it was well implemented, which always helps. In-service results are all one-sided. Outstandingly easy to fly. I mean, it's an open-shut case. We've had people today will tell you that it's easier and simpler and safer from a piloting point of view to do a vertical landing than to do a conventional landing. So we've taken what was hard in a Harrier, vertical landing, and much harder than flying a conventional landing in a normal fighter, and we've leapfrogged conventional landings and made it easier even than a conventional fighter landing. It's so simple. I read an article by a Marine Corps squadron admin officer saying that VSTOL was an admin exercise at the end of the sortie. It was so trivial. We've had former Harrier pilots, literally, I mean, this is unheard of. You know, people don't normally do this sort of thing. Harrier pilots, fairly grumpy sort of old guys, young guys, aggressive young guys, I should say. Thank you for making it so easy, unprompted. And former naysayers, people who opposed this, who were some of the people that we were talking about earlier that were against Unified, are now 100% supporters. So unequivocal success, and it's one of those things that when we were in those dark days and all this emotional struggle and arguments and so on, we're always thinking one day when we've got this in place, people will look back and say, well, why would you ever do it any other way? And that's where we are now, which is quite rewarding. So that's the end of the story on the F-35, but of course what we had did over that period of time and the lessons we learned apply very much to 2 areas that I'd like to cover now as I talk about the present and the future in the time I have left. First of all, what does it mean for electric VTOL? So urban air mobility, you may have seen some of the publications put out by Uber and some of the vehicles that have been in the news, and a very, very exciting new area of aerospace which I'm very, very privileged to be involved in with Joby. But what does what we did before mean for eVTOL? Well, we talked earlier about the military priorities, and of course in urban air mobility we've got commercial imperatives. VTOL is fundamentally hard. We already established that from a piloting perspective. And those issues that we talked about, the military facing, training burden, pilot selection, operational limitations, and accident rate, especially the last, well, they apply even more so in the civil world of urban air mobility. So we have an even greater imperative than the military did to do this right. People talk about autonomy, and we are moving towards autonomy. Who knows when? We can all have our different estimates of when we'll have autonomous vehicles flying passengers. It'll come at some point, but I think there's very few who would argue that we're going to start with autonomous flying taxis. We're going to start with piloted flying taxis. And simplified vehicle operations and mitigating those problems that are inherent to a high workload task such as VTOL flight are absolutely essential for us in the industry. And it's interesting to note that this is not just about VTOL. These concepts of highly augmented control and of giving the pilot direct control of the output variables that he needs to control for that task are spreading throughout aviation. So in the US Navy, we have a flight control strategy. It was named Magic Carpet. And this was developed by one of our colleagues on the VARC Harrier research program. And he simply turned the same concepts to a new problem. He took the same ideas that we'd proven and developed in the VARC Harrier for the hover and applied them to the task of landing a fighter aircraft on a moving, pitching, rolling ship at night, which was, until very recently, by far and away the hardest piloting task in the world. So hard that highly experienced pilots, friends of mine in the US Navy, would go off on a mission, whether it be a real or a training mission. If they're at night, coming back to the ship at night, they'd spend basically the whole hour and a half of their mission worrying about what they had to do at the end of the sortie. That might sound extreme, and you can paint it in different ways, and everyone's a little bit different. But there was this significant sort of threat hanging over you. You've got to come back to the ship at night where you can't see everything except this little dot of light, and you've got to close the loop around your glide slope using intuition and raw handling skills. Super, super high workload. Any of you in the room could now do this with probably half an hour's instruction. It's so simple. Why? How? By applying intelligent design to the problem. That's all. And not asking the human being to do something that the digital computer is fundamentally equipped to do for us. The FAA are conducting groundbreaking research, and the EasyFly concept in flight level engineering's variable stability aircraft there, designing not for the pilot but for the operator, for someone who's not a pilot to come in and operate an aircraft safely and easily, radically transforming the ease with which someone can learn to fly an aircraft safely. So in this context, how can we be thinking old school? How can we be thinking about the way we've been operating for the last 20 years or even the last 10 years with GPS perhaps? There's still lots of things we're doing where we're denying the pilot the ease and safety that we could give him. So because necessity is the mother of invention, I mentioned that earlier, we had a problem with the Harrier, so we solved it for the F-35. Well, we've got a problem in urban air VTOL because we've got to do it safely, we've got to do it cheaply, we've got to do it robustly. And so as a result of this, I believe it's my prediction that the urban air mobility world will lead the way in future PVI development, pilot vehicle interface development. Because we're doing it, Joby Aviation's doing it, our colleagues and competitors are doing it too. And it's very pleasing to see, again, because we have to, that we're going to be leading the way in that area. But the last part of my talk, and I'd just like to touch on part 3, is what about the future? With what we've learned both on the Harrier and the F-35, and with what we've learned with Magic Carpet on the US Navy, and what the FAA are doing with the EasyFly concept, does the CTOL or the Part 25 world now have a challenge to face up to? The counterpoint is we don't have a problem. Commercial aviation is the safest form of transport on the planet. And it's true, and it's an enviable track record and something to be very proud of. And I heard a very senior person in the FAA just within the last week or two quoting in the last 10 years in the National Aerospace System, there have been 7 billion individual journeys, 90 million commercial flights, and 1 fatality, which actually is not quite true, but let's just say it is. Is that a relevant statistic? because you need look not very far to find them. You need to only look outside the National Airspace System to find, in last year alone, 534 fatalities. Air France 447 in the South Atlantic, the very famous and tragic crash just 10 years ago this month. So these accidents, they may be outside the US National Airspace System, but they're in our aircraft. They're in US and European manufactured airliners. It's our problem. Not all of them, but a fair chunk of them. And if we look beyond the 10-year point, it was only February 10 years ago that the Colgan Air commuter airline crash, when the pilot had a stall warning and pulled back on the stick and pulled back on the yoke in the stall. So I don't think the problem is solved. Yes, it may be the safest form of transport, but we can make it safer still. So if we're doing something wrong, what are we doing wrong? Well, I think what we're doing wrong is fundamental to the challenge of automation. We need to consider as well, not just the flight control system that I've been talking about so far, but the pilot-vehicle interface in general. And with automation, we've made the flying task in a Part 25 airliner really, really easy, 99.9% of the time. And as a result, we've dumbed down the pilot. And this may be controversial, but I'm afraid it's true. We have dumbed down the pilot by making his task easy. You know, call sign ABC, proceed direct, Sierra Foxtrot Oscar. What's he do? That's how we fly today. Call sign 1234, you're cleared the ILS approach runway 20 San Francisco. It's already in the FMS. So we've dumbed down the pilot. And yet when things go wrong, we expect him or her to save the day. It's a deep flaw. Sometimes we get away with it with some exceptional skill, Hudson River. Most of the time we don't. So is the solution, as some people are saying, and as some people have been saying for some years now, to limit automation and give more back to the pilot? So we bring his skill level back up? Absolutely not. That is the dumbest response to what we've seen in these areas. No, the solution is to do automation right. Is to automate, but to finish the job. The argument is not against automation, it's against partial automation. We can save the pilot from him or herself. We can, as I like to say, wrap the pilot in cotton wool to prevent him or her making the errors that we know people make. For example, we still have direct link modes in our airliners today. So we have a nice super-duper fly-by-wire flight control system, but if some sensors fail, we drop back to a direct link, a manual flying mode kind of concept. And yet we've been flying 40 years with the F-16 without any fallback manual flight control system. Now every military fighter has full-up fly-by-wire with no direct electrical link, no manual fallback. So why are we still putting it in our airliners? And we still fail to protect the pilots. I just talked about wrapping him or her in cotton wool. We still fail to protect the pilot from all the mistakes we know human beings make. A pilot can still run himself out of fuel, or herself. A pilot can still fly into the ground or get too low on energy and end up into the ground, or just ignore the GPWS. Yet the military have had automatic ground collision avoidance systems for 10 years. Why are we not talking about that more in civil airspace? And there are a variety of individual aircraft vulnerabilities, and obviously I don't want to get into politics by talking about particular aircraft types that we all know about. But we're failing to protect the pilot from him or herself fully. But we can do so. We can do so. Full protection is realistic. We understand the human being, and we understand the mistakes and errors that a human being can make. And with digital computers today and the incredible power we have in digital computers and the knowledge that an aircraft can have about not only itself but the world around it, makes all of these things practical. We already have the ability to wrap the pilot in cotton wool. It's just a case of approaching the design intelligently with the right objective. In the same way that the US Navy approached the carrier approach task and turned something from the hardest task in aviation to something pretty straightforward, was by taking intelligent design and digital computers and applying them to the task. And we can do that today. The disincentive. I was told this by a just retired, very senior executive from one of the two large Part 25 manufacturers. I won't say which one, obviously. He said the customer doesn't want it. All these things we could do, the customer doesn't want it. So we supply what the customer asks for. And I think that's poor. It's legacy thinking. It's just like the pilots who, back in 2002, didn't want to accept that there was any other way to hover an airplane than having XY control on the stick. We've got people who are saying, well, this is how we do it. No, this is what I'm used to flying. This is what I want it to look like. This is how I want my autopilot panel. And we tinker around the edges, and we make little things better, and we change the disconnect functionality so the autopilot doesn't disconnect so easily. And we tinker, but we don't really solve the big problem. Let me give you an example of pilot paradigm in aircraft design. The P1127, Bill Bedford, a great test pilot. I heard him, privileged to hear him speak before he died. He said, I wouldn't have he was asked by Hawker Siddeley to use a collective lever in the cockpit. So he had throttle, but a collective lever for the hover. He said, I wouldn't have anything so agricultural as a collective. Then the XV-15 came along. It was a rotary wing program, rotary wing personnel. They had a collective. Next, V-22. V-22 program leader or program direction came from a man with a Harrier background. He said, we'll have a throttle, not a collective. Augusta Westland 609, rotary wing personnel, collective. So what's going on here? Is this intelligent, objective design? Or is this just legacy experience driven? Is it just depending on who your test pilot is, what kind of a flight control system you end up with? And I make no judgment of which is right or wrong here. I just use it as an example of the extraordinary influence of pilot preconception or customer preconception and the impact it can have on our design. So I think we should move forward together. The time is overdue to take a radical approach to the role of the human in the cockpit and to apply the digital computer and our knowledge of the human being to the task. We can do it all now. We have the potential to do it all and fully protect the pilot from him or herself. The urban air industry has no choice. Joby Aviation and our colleagues and competitors, we're all pursuing innovative, advanced pilot vehicle interfaces because we have to for our commercial goals. And my fervent hope is that we can move forward together as an industry throughout, from general aviation to Part 25 and everything in between, because there's work to do, and actually it's not that hard. It just requires some careful, objective thought and intelligent design. I'm going to finish with a little video, which is If You Do It Right. It's a video of a news program. This is the national news in the UK, and we actually had a science editor for the news channel come out and fly the VARC Harrier, and it's quite entertaining. And I'll just finish on this note before wrapping up.
Now, the RAF claim that flying the latest Harrier jump jet is as easy as driving a car. Well, we were a bit doubtful about that, so to put it to the test, we sent them our science editor, Lawrence McGinty. Now, Lawrence actually can't drive a car, but despite that, they still let him loose at the controls of a multi-million-pound jet fighter. Here's what happened when Lawrence became our very own Top Gun.
I walked across the tarmac with test pilot Chris Gopka, but I still couldn't believe it. They were going to let me fly a Harrier. As they strapped me in the rear cockpit of the two-seater experimental plane, I kept telling myself the new control system made flying the Harrier easy.
I'm fat, I'm 50, I'm trussed up like a chicken, I can't even drive a car, but I'm going to have a go at driving this.
It was reassuring that Chris, who's flown Sea Harriers for ages, could take control instantly if I screwed up big time. He flew the takeoff, and it took my breath away.
Oh my God!
Only a few minutes into the flight, and Chris hands control to me.
Press and hold, this is the engage button now.
Engage, yep.
On the interceptor, I'm pressing and holding now.
Okay, you have control of the aeroplane. Okay, so if you want to just push the nose down a bit, you might as well push the nose down.
The new system is easy. Push forward on the left grip to go faster, pull back to slow down. On the right, forward to go down, backwards to climb. Left to go left, right to go right. After 5 minutes of flying the Harrier, then came the tricky bit, bringing it into a hover and landing vertically.
Here we are, we're jetboarding an aeroplane, which is quite spectacular, and we're at 100 feet. So all I need you to do now is push forward on the right stick. Okay, just ease off on that rate of descent, thank you. Just keep coming down there. There you go, that's perfect. Keep coming down, keep coming down, keep coming down. We're on the markers, or close enough to the markers for me to be happy. Keep coming down, keep coming down, keep coming down, keep coming down, keep coming down.
And you've got it now.
I've got it now. Many congratulations.
I don't believe it. That was oh, wow.
Very well done.
How do you find sex interesting after this?
Now the RAF
He was a real character, a very good presenter. So that more or less concludes my presentation. We'll turn over to Q&A in a moment. I'm asked all the time about Joby Aviation, so just a quick postscript to cover the questions that I can answer. We currently remain out of the public eye. I hope we'll be able to go public soon, but we currently don't release information, and so I can't really say much more than what I'm going to give you here. What I can say is we've successfully flown full-scale demonstrators. Our production vehicle will have safety assurance in excess of Part 23 requirements. Obviously, unified flight controls. We'll do a 200 miles an hour cruise, 150 nautical mile range, and it'll be very, very quiet. We are looking for a few good people, unabashed pitch here, particularly system safety engineers to help us do what we've been talking about, electrical avionics, test, and manufacturing engineers too. With that said, that concludes my talk, and I'll be very happy to take any questions. And I think Roddy's going to too. Thank you.
So before we take questions, I want to thank Justin again for such a wonderful presentation, and to steal some of his friend Pete Wilson's thunder. That was awesome. That was a great presentation. Congratulations on the award. I think we want to do the medaling before we do questions. So with this.
Thank you very much. Thank you.
Congratulations. And we do have about 10 minutes for questions.
Okay, Justin, thank you so much for coming. What a great presentation. Question is, yes, it is very easy to say, you know, the time has come for us for unified controls and for AI to take over and all that. That sounds all great, but there are plenty of instances where you see, like if you remember the Airbus Airbus 321 that flew into the trees because the pilots wanted to climb, and the airplane just kept on going into the trees. And obviously, more recently, hate to say it, but the Boeing 787 instances are all over the news, and you know what that's all about. So the bottom line is, I cannot help but be skeptical to allow the computer to take over when you see situations like that are very public, they are very dangerous, they are very impacting to the aviation community, and I don't know how we all can always, Space Odyssey 2001 comes to mind, the computer's taking over and everything, so all this stuff is very scary for legacy folks like me that are getting very old, but at the same time, we cannot get away from being conservative. So anyway, I'll give you the floor. Thank you, sir.
Thank you. Yes, so excellent question, thank you. I don't want to speak about the 737 just because it's so topical. But let's talk about that Air France one where he went in the trees. That was entirely avoidable with some intelligent design in there. So aircraft, they know about the ground. They know where the ground is. They know about their energy state. They know about their trends. They know how long it takes to spool up the turbofans. Stuff that the pilot didn't compute. So he got himself low with the throttle back at idle, and the spool up time on the turbofans was too long. And he messed up and they ended up in the trees and people died. That's exactly the sort of thing that we can avoid with intelligent design. The airplane knew everything about that situation, and with the right algorithm in there would have avoided that. We can avoid an airplane allowing itself to get into a corner position like that, because it can look ahead 100 times a second or whatever the update rate is in its control system, and project itself ahead and see, hang on, pilot, you're about to fly me into the ground. I'm spooling up the engines. just as it does in an Airbus when you hit the alpha floor anyway, but there's a lag in the engine. So all we needed to do is to bear in mind the terrain. So if there hadn't terrain hadn't been there, he'd have been fine. He wouldn't have stalled, because the Airbus doesn't stall, at least when it's in full up flight control. But by bringing the terrain into the equation, we could have avoided that accident. And that is true of almost, I challenge all of you, give me an example that can't be solved with a digital computer of an accident of that ilk where the pilot was not protected from his own error. Anyone? So we can do it. Believe me, we can do it. Every example, we can think through it and design an algorithm to prevent someone from getting into that situation.
Hello, Justin. Great presentation. Wanted to ask you about fault-tolerant architectures and how you see having a fail-safe system be a part of this easier-to-fly concept. How that relates to the grander picture, and maybe to answer the first gentleman's questions about helping us feel at ease.
Yes. I haven't spoken at all about the redundancy and reliability of these systems, which obviously underpins everything. That I alluded to it when we talk about partial automation and then handing the situation back to the pilot when things go wrong, which is exactly what we don't want to do. So you need to have sufficient redundancy underlying these concepts that they are going to work 10 to the minus 9, risk of failure. Some would argue that some of the airliners have direct electrical links or direct laws or backup laws because we need to mitigate for sensor failures, which will make them revert to those backup laws. But the alternative is not to have the backup and to design sufficient redundancy in the first place. The risk of needing direct link or direct law is far lower than the risk of the pilot messing it up if he's given it. And that's the counterpoint. We can make the risks of failure by designing sufficient redundancy far, far lower than the risk of the pilot messing it up when it happens. Does that answer the question? Is that good?
Hi. Great presentation. Thanks a lot. So I was wondering, do you think there's going to be a day where we won't need pilots at all, where it'll be fully automated?
Yes, undoubtedly. And I think it'll come first in the urban VTOL world because payload is so pressing there. And so the economics of the urban air mobility market, as it's called, are hugely changed by being able to pull the pilot out and put an extra passenger in there. Not just the pilot costs as well. I mean, not just the payload requirements, but also the cost of training and handling pilots. I think for commercial airlines, Part 25 type aircraft, it'll come as well, but later because there's less of an imperative. When you've got 150, 200, 400 people on board, it's not so much of a proportionate impact to your bottom line to have a couple of pilots at the top. But it's definitely coming, and I think in the urban world it's going to come far sooner than many people realize, because there's so much pressure. Whenever you have a problem to solve and economics behind it, and the market is seen as huge for urban flying taxis, because of the pressure and the focus on this, it's actually moving quite fast already. People are working towards it. So it'll definitely come. If I was a betting man, I'd say it'd be within 10 years. And it might be much short of 10 years for the urban market.
Hi, Justin.
Hi.
Nice tie, by the way.
Thank you.
Great presentation. Automation depends on software. Yep. So how do we ensure, and the software and the automation and the scenarios are pre-programmed. They are thought through. But how do we plan? How do we deal with the unexpected? Because as we throw more and more software at aircraft in the future, the likelihood of bugs being introduced into software is always there. And how do we mitigate that?
Well, I'm not a software engineer, so I can't answer in any detail other than to say that we have obviously already developed processes to validate software and regression testing, and there are lots of techniques, and clearly those become more and more important. And we do come back to this point that we have to design these systems, however we have them. If we're going to follow this kind of a strategy that I'm espousing, we have to design the system to be reliable enough that it doesn't need the pilot. But we have to make sure that, as I said to Borja, the chance of the system failing is far lower than the chance of the pilot making a mess of it if we're relying on him as a backup. And as soon as we've crossed that barrier, then it's easy. Safety lies on the side of going the automation route. because neither is perfect. So a bit of a glib answer, but in summary, there's lots of very clever software people that understand software verification and validation and so on, and we have to do more and more and more of that, and we have to be sure that we're reducing the risk of failures there to an absolute minimum. I hope that wasn't a cop-out.
I wanted to follow up with a question. You didn't have a chance to explain it very much. Could you talk briefly about the safety monitor that was used on the VOC carrier and how that was used in your testing strategy?
Certainly. So the safety assurance for the VARC carrier, as I explained, the experimental flight control software that we were flying and evaluating was totally untested. Well, not totally, but could be totally untested. The assurance of the vehicle safety was through two routes. First of all, a safety pilot who had conventional Harrier manual controls, so that if the flight control system, the experimental malfunctioned, he could just take control straight away. And the second is that we assisted the safety pilot with something called the independent monitor. And the independent monitor was a separate flight control computer that was sort of a guardian of the flight control envelope. It was like envelope protection. It looked for failures, so it did A versus B cross checks, and if we had A versus B sensor failures, it would trip the experimental system off, but it would also look for envelope excursions or a trend towards the boundary in the envelope. So if we had an alpha limit of, say, 10 degrees, if we hit 10 degrees statically, we'd trip off the experimental system, safety pilot would have control. And if we had a rate of pitch towards 10 degrees alpha, we'd trip off a little bit earlier to give the pilot more time to handle the overshoot in pitch. And so developing the independent monitor was a chunk of work on its own. That was about the first year of my work on the program. It was flight testing and proving all the limits of the independent monitor and attacking its protections to make sure that it tripped off in time to give the safety pilot time to recover. I'm afraid that there's a lot to try and cram into 45 minutes, so much remains untold. Thank you.
Okay, so I guess that wraps up the lecture. Congratulations again on such a great honor.
Thank you very much. Thank you. Appreciate it.